All right, so third part of probability. Another way to organize our data is a tree diagram. So quick example here. Here's a study done by the Harvard School of Public Health on the college students there on campus. 44% of whom admit to engage in some type of binge drinking. Obviously, these folks are of age. 37% said they at some point drink moderately, and 19% of the students there say they don't um, drink at all. A further study finds that among the binge drinkers, 17% are involved in some type of alcohol-related accident, and we're going to go ahead and say that that it's their fault. While among non-bingers, which for us in this particular case, if they're not binge drinking but they're still drinking, really this is just the moderate drinkers. 9% of those folks have been involved in alcohol-related accidents that we're going to call their fault. So what makes this a little bit different than what we've seen before? Those two sentences, among binge drinkers, we've taken the big group and we've kind of narrowed it down, right? So let's say that this was all of our students on campus that are in this study. Um, what they're saying is we've essentially kind of started to separate into smaller groups. So here's all the students in the study, and we've decided, all right, we're going to separate all of the binge drinkers. Are going to come over here, and so out of these binge drinkers, we're going to figure out the probability that out of this smaller group, how many of these folks, what's the probability these folks have had an accident? So when we're taking that subset, when we're taking that smaller group like that, what we're essentially doing is running a conditional probability. So the fact that conditional probabilities are popping up in this thing make it a little bit more interesting. So the first thing that I suggest we do here is take all of these statements up here and turn them into probability statements. So the probability that we get a binge drinker, 0.44. The probability we get a moderate drinker would be 0.37. The probability we get somebody that's abstaining from drinking, 0.19. And now let's go ahead and turn these conditional statements also into probability statements. So this is the probability we know that we have a binge drinker, that they've had an accident, and that's going to be 17%. The next probability, out of the moderate drinkers, given that they are moderate, what's the probability they've had an accident? And that's 0.09. So what we can see here with the conditionals getting thrown around, different than what we talked about previously. We're going to need something beyond just that two-way table. This is where a tree is going to help us out. So let's carry over our information from the previous page, right? Here's all our probabilities. And we're looking for what's the probability a randomly selected student will be a binge drinker if we know they've had an accident. So here's one of those situations. We know that we're pulling from the group that's had an accident. So as a probability statement, right, we know the student has had an accident. So out of those accidents, we want to figure out the probability that that's a binge drinker. So again, if you got your student population this time, we're actually going to say, out of all you guys that are in the study, what we're going to ask is that all the folks that have had an accident grouped together. So this could be people that were binge drinkers, moderate drinkers, um, or maybe even the folks that abstain. Everybody that's had an accident come over here, and then out of this group, we're going to figure out the probability of those folks, or the proportion of folks in the accident subcategory that have had an accident, or that are binge drinkers, excuse me. So our best way of doing this is to go ahead and set up a tree diagram. So the first split is what type of drinking these folks admit to. And so we got the binge drinkers, the moderate drinkers, and those that abstain. And then from there, we've got two situations. The binge drinkers could either have an accident or not have an accident. So we know that 17% of the binge drinkers have had an accident, which means out of the binge drinkers, 83% have not had an accident. Out of moderate drinkers, 9% of the moderate drinkers have had an accident, which means Out of just the moderate drinkers, 91% have not. Interesting way of looking at this one down here at the bottom, if someone does not drink alcohol, the probability that they have an alcohol-related accident that's their fault is 0. Basically, the people that abstain, there's no way they can cause an alcohol-related accident. So let's go back up here to what we discussed before. The probability, if we know that they've had an accident, the probability that they're a binge drinker. So once we've got our table set up, or our tree set up, and once we can translate all of this up here, once we translate this into a probability statement, the difficult part's over. Now we just follow what we've done so far, and we know that the conditional probability would be the probability of a binge drinker and they've had an accident over the probability that they've had an accident. So binge drinker and accident would put us at 0.44 times 0.17. Now what's interesting, when we go to accident, if you look at your tree, there are 3 situations where you could have an accident. You could be a binge drinker and have an accident, a moderate drinker and have an accident, and I'll mention it here because it's part of the tree, but you could abstain and have an accident. Obviously with a 0 there, that can't happen. So there's 2 ways to have an accident. You could be a binge drinker, or you could also be a moderate drinker. So with that or, we're going to have a plus in the middle. So the binge drinkers and accidents. Right, so there's the probability of binge and accident. And then this, 0.37 times 0.09, this would be the probability of a moderate and accident. Right, so this is where the tree is extremely helpful because we basically just have to figure out exactly where all the different scenarios are within the tree. So at the end of the day, when we go ahead and just plug all that good stuff into the calculator, we get 0.69. About 70% of the alcohol-related accidents then were caused by binge drinkers. So one of the great ways to check if your tree is set up right is to find the probability at the end of every single branch. So for example, 0.44 times 0.17, this is 0.075. Binge drinkers that have not had an accident, 0.44 times 0.83, 0.365. Moderate drinkers, 0.37 times 0.09. So this would be 0.033, 0.37 times 0.91, 0.337, and then here's 0.19. So just as a quick heads up, what this probability is, this is the probability that we get a student that is both a binge drinker and has had an accident. Another way to think about this, 7.5% of the students on campus would say that they've done binge drinking and they've had an accident that was their fault. 36.5% of the students on campus will admit to binge drinking, but they have not caused an accident. Right? They have not caused an accident. 3% would classify themselves as moderate drinkers and have caused an accident, while 33.7% are considered moderate drinkers, but they have yet to cause, or they haven't caused, I should say, an accident. Again, this kind of makes sense too. There are no students on campus that don't drink. Right? The probability that we get a student that abstains from drinking and causes an alcohol-related accident, that can't happen. That's why that's 0. So are there people that have abstained and haven't had an accident? Sure. So what this tells you is 19% of the campus are students that don't drink and have also never been in any kind of accident. So, or any kind of accident related to alcohol, I should say. So what we can do with our table now is we can take a look at one more probability. Right? Let's say we wanted to find the probability that, let's say we wanted to find the probability that we get a moderate drinker, given that we know that they've never had an accident. Right? So knowing, right, we kind of subgroup. We want all the people that haven't had an accident. How many of those folks are not drinkers, or moderate drinkers, I should say. So clean this up a little bit so we can see everything better. Okay. The probability of moderate and so this would be the probability of moderate and no accident over the probability of no accident. Right? So the probability of moderate and no accident, right? So basically 33.7% of students are moderate drinkers that haven't caused an accident. And then no accident, there's actually three ways to not have an accident. You could either be a binge drinker and not have an accident, a moderate drinker and not have an accident, or you could abstain and not have an accident. So the issue here is we've actually got three numbers to put together in the denominator. And when all is said and done, once we get this, the probability that we get a moderate drinker out of those that have never had an accident is about 38%. So essentially, 38% of the folks that have not had an accident are moderate drinkers. That's where that kind of falls into place for us. So one way to, a quick check to make sure that your tree is right. Always good to kind of point this out to you. Each step along the way, we've got a probability rule that says, the sample space should add up to 1. Well, that's a great way to check to make sure your tree's set up right. The first branch, these will sum to 1. As you go out to each individual branch, all of these should also sum to 1. So at each branch, you should get sums of 1. And then the final check to make sure your tree's set up right, if you do the full branch, if you multiply those things together to figure out the probabilities in the end of each branch, these again should sum to 1. So as you're setting these things up, that's a quick check to make sure that we set them up the right way. So let's say that we look at one more quick example. 2005, this internal medicine suggests that if folks had HIV, 99.7% of the tests were correctly positive, while for people without HIV, 98.5% were negative. Clinic in an area says that 15% of the patients in that area probably do carry HIV. So what's the probability of a patient testing negative, if it tests negative, that they're truly free of HIV? In other words, right, this is probably a bit more applicable than the one with the drinking. Right, now all of a sudden we're talking about false positives and false negatives. In the medical world, probably a little bit more applicable, I guess we could say, to the real world. So quick look at some of the probability statements. Right? If they have HIV among those with HIV, so out of that subgroup, 99.7% of the tests, so the probability that they test positive given that they have HIV is 0.997. If they do not, out of that group without HIV, right, no HIV, a negative result is 0.985. And then the other probability, we think that 15% of the people have HIV, which means that the people walking in, that means 85% of the folks walking in do not. So just so we have the same letters the whole time through, all right, we'll say P is for a positive test, and that would mean that the opposite of P, or P, we'll use P with that line over the top to be our negative test, and then so there's your setup for all that. So this would be the probability again that somebody with HIV test positive. So quick set up the tree. So we're pulling out of the group, they either have HIV, right? This would be have HIV, and this would be those that do not have HIV. So on the chart, we can see that from our problem, 15% had it, 85% didn't. Now, whether or not they have it, the next split is going to be whether or not they test positive. For those that have it and test positive, it'd be 0.997, which means there's a small group of people out there that have HIV and test negative, right? This would be a false negative, and that's 0.003. If they don't have it, probability that they test negative 0.985, which means there is a small group of people out there, right? There's this 1.5%, right, that do not have HIV that test positive. We'd call that a false positive. So the question that we're being asked, what's the probability that a patient tests negative that they are in fact truly free of HIV? So in other words, what we know about them is they've tested negative. So that's given that their test is negative, remember not P, not positive is negative, what's the probability that they do not have, if they don't have HIV, right? Different than up here, same letters but different order. Again, once we have a tree, and once we have our probability statement, we're in business. What I'm going to do is take a quick second and fill out the probabilities at the end of my tree. This is 0.14955. This one's going to be 0.00045, 0.85 times 0.985, 0.83725, and really this is just to save me some work from having to type in a bunch of stuff in my calculator. 0.01275. All right, so I've got my probability statement set up, right? That they have tested negative, that they're truly free. So this would be the probability of not H and not P over the probability that they have tested negative. So let's plug in numbers. H and not H and not P. There's that value right there. 0.83725 over, and again, there's two ways to test negative. You can either have it and test negative, or you can not have it and test negative. So 0.00045 plus 0.83725. So take a quick second, think about that. If they've tested negative, there's probably a really good probability that they don't have HIV, that we get a true positive or true negative, I guess, in this particular case. So plug and chug into the calculator very quickly. Divided by. So basically what they're telling us is 99 point, I'll round properly, 99.95% of the tests that show up negative are folks that are truly free of HIV.